we can predict the concentrations of partial pressures of species at equilibrium, given the balanced reaction, initial concentrations or partial pressures, and the known equilibrium constant. So here we construct an ice table, and before the reaction initiates, we have 0 concentrations of the products. And the reactant A gets consumed, where X is an unknown concentration. And for every mole of A, 1 mole of B gets consumed. And 2 moles of C get produced, and 1 mole of D gets produced. Then we add these together, and then we write the equilibrium expression using the unknown concentrations raised to the stoichiometric coefficient. And the concentrations of the reactants go in the denominator. And given the equilibrium constant is known, we can solve for X and then substitute into these expressions to obtain the equilibrium concentrations of the reactants and products. And you may get similar problems involving gases and partial pressures rather than concentrations. Determine the equilibrium concentrations of the reactants and products in a 0.1 molar solution of acetic acid, where the equilibrium constant is given. So here we set up an ice table where the initial concentration of the reactant is given, and before the reaction initiates, the concentration of the products is 0. And for every mole of acetic acid that's consumed, we have an unknown change in concentration, and using the mole ratios, we have the same unknown change in concentrations of the products. And then adding these together, and the equilibrium constant can be written in terms of the concentrations of the products raised to their stoichiometric coefficients on the concentration of the reactant raised to its stoichiometric coefficient, which can be simplified as follows. And the equilibrium constant is given, and to avoid solving a quadratic equation, we can apply the approximation that the equilibrium concentration of the products is mostly insignificant compared to the initial concentration of the reactant. So therefore we can get rid of this X in the denominator, and now we can solve this equation much easier, which gives the following value for X. So that's equal to the concentration of the products, and then subtracting from 0.1, we obtain the equilibrium concentration of the reactant. And you can verify that this approximation is valid by substituting into the original equation and verifying that both sides are almost equal.